Good evening, everyone. So I'll be talking about uh, innovative hydraulic design and solutions and how to deliver reliable and equitable water to every household in India through pipe water supply. Although I'm presenting, but at the back of this entire work are two of my PhD students. One has graduated, Dr. Anush Kumar Ghorpade, and Abhishek Sinha, who is a senior student, a PhD student. So with their lot of dedication and hard work, whatever work that is achieved, I'm presenting. So and there are many other supporting staff, and our center is there, who is basically outcome of this particular research and development is because of all of these people. So uh, let us start with the topic. So let us first understand the current reality of water supply systems in India. Water supply in India is intermittent, ranging from 30 minutes to 12 hours per day, whether it is urban or rural. There are many cities in India where alternate day water supply is there. There is cities which is once in a week or fortnightly also people are receiving water. So we have inequitable distribution embedded in the system. So in high level of intermittency, high level of inequitable distribution, coverage through different programs. Our government is trying to achieve more and more coverage, but coverage may not guarantee you the again the supply. Pipes will be there, but you may not receive water, and we will see the reasons for that. And situation is similar irrespective of water availability. What I mean is that even if there is a water, you may have intermittency, and that's the scenario in many locations. So intermittency can be of variety of reasons. There may be lack of water availability at the source, and there may be some other management issue, technological issues, which are because of which you will have intermittent water supply. So the root cause of the miserable low supply is the entire management problem of water is wicket problem. That means you try to do something and there will be cascading effect that you try to fix something and something else will emerge as a next problem. So let us understand how this entire problem has become such a complicated situation and what can be the small steps we can do towards fixing this problem. I have studied these water supply systems across definitely Maharashtra, which is very local to us here. But even in other states like Telangana, Rajasthan, and variety of places I've been visiting as in different roles. West Bengal, a very good response we have from West Bengal Public Health Indian Department. We are closely working with them for improving water supply systems. So based on all of this understanding that we have developed in last 1 decade, you can say, I'm going to present this work. One example of wicket problem is water losses. You can see there are water losses available in this particular entire system that we are running. As per the manual, 15% losses are admissible. That all of you know, all of you are water practitioners. But we have 30, 40, even 50% of water losses in many situations. Now, one question is whether it is effect or a cause. Because many will conclude this is the effect of poor management, but it is also causing and reinforcing the water losses itself. So we have basically attached in a particular a situation where determining what is the effect and the cause is very difficult. So we have to look the problem holistically and without shooting some solutions at a large scale, we have to work at a stepwise manner. And we have to look at the entire pathway of provisioning of domestic water in a very, very holistic way. As I told, water management, wicket problem and one size fits for all will not work in such situations because there are long-term technological lock-ins, social lock-ins. That means if you lay a particular infrastructure, it will remain for next 30, 40 years. There will be social behavior that will be developed. It will be very difficult to change. So social aspects has to be really considered. Many people advise 24/7 as a one solution for problems of water in India, but how it is fitting to our situation is very difficult to understand. Even the developed countries are facing issues with respect to achieving 24/7 water supply. So I have not seen a replicable and self-sustainable model for across India to be replicated. There are threats of emerging contaminants like pesticides, pharmaceuticals, microplastics, heavy metals, which will definitely make households depend on water filters. So we have to look really whether we have to treat entire quantity of water to a high quality drinking water, pass to the pipelines, which will again recontaminate it. So a lot of research is also happening and discussion is happening even in developed countries to do point of use treatment. That means treatment at the house, because this entire system is very resource intensive, very difficult to sustain. So focusing on treating the required quantity for human consumption, we have reached to that particular level that we cannot afford now because of the energy consumption, because of the let's say revenues that are required to operate these systems, to treat entire water to the purest quality and again pass it through the pipelines, which will contaminate, whether it is 24/7 or intermittent contaminations chances will be there. So people will be depending on household water filters. How we can make use of that opportunity, we have to look at that way. So diverse and distributed water provisioning systems with circular economy approaches, modular treatment systems, enhancing resilience, those are the directions on which we should look for. So future urban water infrastructure should basically, I'll propose to walk a path of scaled decentralized systems rather than centralized systems. What we are doing is creating a very large centralized systems, which are very difficult to operate and maintain, and which are not sustainable and resilient. So one of the paper that I wrote in a recent IWA journal, policy journal, that we need to entirely rethink how we're planning our entire water cycle. And you cannot segregate water supply problem from sewage treatment or recycling. It is all interconnected in today's time. So let us, so those who are interested can follow this paper. I will not be talking about this today, but I will focus only on the water supply part, but the connections we have to remember. So what has happened, we are trapped into a vicious cycle of water supply. That means you start from any point. You start from any point like this, you will reach again back to this, and we'll see how. Because we are planning is not correct. Our designs, there are tremendous issues in the design. Our analysis methods are not correct. That leads to a poor service quality. What is poor service quality? That means supply hours are reduced. We have low pressure, we have inequitable distribution. So there are issues with the reliability of the system. So people are not willing to pay. So consumer satisfaction is a very low. So how we can charge a tariff then? Because if consumers are not satisfied, our revenues will be low. We cannot have telescopic tariffs. We cannot have the good tariff system. So ultimately, it will lead to poor operation and maintenance. Again, lower supply duration. So we are basically reaching back to the, so no amount of new infrastructure if we keep pumping, and that has happened for last 2-3 decades without looking the problem at holistically. We are just installing new pipelines, tanks and pumps and motors. That has not resulted in a good manner. And we are trapped into the this particular vicious cycle of water supply system. So we'll see how to approach this particular problem when we are stuck with such a complexity. So we have documented all these drivers for intermittent water supply. This is open source paper, so anybody can read this. So basically all the drivers we have to understand and then plan the strategy of how to address the water supply situation. What we are doing currently is we are planning our pipe water supply using this particular framework. What we have is we have a source, maybe river, lake, groundwater. We pump it or gravity, bring it to WTP. We have master balancing reservoirs. We have ground service reservoirs. We have elevated service reservoirs. Some people have some pump distributions. We have different kind of consumers, residential, commercial, and institutional. But actually, in reality, we have such a huge density of people living in cities now, and variety of mixed land use. There are commercial, there are residential, there are institutional. So, and with the huge storages. So, which is makes the whole design very complicated. So what is expected from water supply engineers is to supply water from different norms, 135 or 150. For rural areas, it can be 70, 55 in Jal Jeevan Mission. So one is quantity, consumption pattern. Right now, the design assumes a consumption pattern typically like this, which will allow water to draw in a peak hour, but this never get exerted. That's the whole tricky part of the design. Although we design in this particular manner, but it never get realized on ground. Why we'll see in some time. So residual pressure criteria is 7 meters. I have not seen any DPR more than using this 7 meters criteria, and we have not achieved 7 meters. If you go and take pressure across the city, I have not seen many cities with such a achieving 7 meters first of all. So we have to investigate first of all why we are not achieved 7 meters of pressure. We are designing for 30 years and we have to design it for 30 years because it's a public infrastructure. It will remain there. So instead of centralized focus, we can have decentralized systems, and which will allow us to, with a smaller investment, to rechange and refurbish in coming time as per the requirement and development. Admissible losses we have to maintain up to 15%. And then we have water quality to be maintained. And I given in the first, water quality, we have to relook entirely, whether we want to transfer the purest water in the pipes or not is a big issue. So remember, all of this is achieved for 24/7. It is written in CPHU manual of 1999. So why we are not achieved? Let us understand. Okay. So question is, why we are not able to achieve 24/7 water supply? So if many people talk about, now pump distribution and use pump distribution for the cities, by looking at the Western countries or developed countries model. But one point we're forgetting is we have to use this system when we can control the demand or the demands are defined. In cities like ours in India and developing countries, demand is very unpredictable. So typically what is expected is that average flow will come from this, and during the peak time, water will be coming down from this floating reservoir. This is floating reservoir. That means it has single pipe. Inlet and outlet is same. So during peak time, water will come down, and during night time, when there is a low flow, water will basically filled up in this. We have not tried this model in India. There was some example in Yavatmal in Maharashtra, but documentation is missing. It was very old in 1980s. And this particular system works at a very high pressure. So basically it is designed to take care of maximum day, maximum hour, and also fire flow. So in developed countries, this is the model people are following. Now, can we adopt this particular system? Why not, right? Let us understand why we are not adopting them. The residual pressure criteria in this particular countries is 17-15 meters. And if you see, they have good governance, they have good, let's say, affordability. In Indian socio-economic context, who will bear the cost is a big issue. So it's not a technological challenge to provide water at a high pressure. It means anybody can very easily design. If you give a infinite amount of resource, put good pumps or floating reservoirs, and try to provide a city with the high pressure. Issue is whether we can make it affordable for all, whether this will sustain for a very dynamic nature in our cities where governance is very poor, where monitoring is very poor. So there has been many effort of 24/7 throughout last 1 or 2 decades, but no, those are not successful. And I have not seen the designs are correct. The designs and configurations are not correct in those installations. So we have to understand this particular system, and what we have adopted is a half part of this in whatever 24/7 projects we have done. So in Indian water distribution layout, mostly what happens is, whether it is gravity or pump, we pump it to the elevated storage reservoir and then supply to the city. So the entire demand is basically supplied through reservoirs, and we have typically 1/3 of this particular volume as the demand stored in this particular reservoir. Now what happens is, these cities do not have any control in the withdrawal. They have storages, there are no metering, people do not close the tap. So tremendous amount of withdrawal happens through this particular system. And we are working with 7-meter pressure, which is not yet achieved. So very long distance we have to follow if you have to raise to a higher pressure. So what is happening because of this is, although we design our system at the low supply level here, and we assume that when the tank is full, at least we got a good pressure in the city center, that is not happening. Because what is happening is, because of tremendous amount of withdrawal, these tanks are basically not coping up with the supply and demand pattern. Whatever assumed in the DPR is not a reality. And I will show in some time what is happening in the design and analysis. Because the withdrawal capacity, we have to understand the withdrawal capacity of the network. What is the withdrawal capacity? The total number of connections that are trying to fetch water as soon as this wall is opened. So as soon as this wall is opened, all the consumers are ready to withdraw water, which was not assumed in the DPR, right? The DPR assumes that only in the morning people will be waking up, many people will be waking up and consume the water. So we have a basic design and implementation or operational difference. So tanks get immediately empty. In 30-40 minutes, tanks get empty. In many cities I have seen, people are bypassing the tanks. In rural areas, cities, where I have seen people are bypassing the tanks. Tanks are standing empty. So further, the HGL drops to the standing water column. So I'll explain the concept of standing water column that we have introduced. So the actual operating level is in between somewhere. Okay, somewhere which needs to be determined. It is not as per what written in the design. So this is one experiment we did to show what happens to the standing water column. So when this particular inlet flow is limited, you cannot increase the inlet flow beyond one limit. Like this is decided by pump or head available at the upstream. So what happens is when you have the higher withdrawal from this particular point, the actual HGL drops below, and there is an air entrapment. So this needs to be understood when we analyze our intermittent water supply network. So even if you can see how much air is getting induced, and for a bigger diameter pipelines, you can imagine how much. So this is our students have done this kind of analysis, and based on this, our analysis methods are developed. So what is happening? Our tanks levels are remaining low. Those are basically causing tremendous amount of problem. So we conducted actual validation at the one overhead reservoir ESR at the Dhanu city in near Mumbai. Tank was of 7.5 lakh capacities, which is having 16 meter staging height. So what we observed is after let's say 30 to 40 minutes, there is a tremendous drop in the level. So initial level is about 18-20 meters. At this point, you can see the pressure gauge here, and after this particular point of time, the water goes below the tank level. So tank level is marked here. So water goes below after 40 minutes than the tank level, which is the confirmation of standing water column. So this kind of number of observations we have from the field. So based on that, what we how we respond to on the ground is how our operators are responding in the cities is they have these tanks lying up like this. This is from a real city from Maharashtra. Where we have mapped some of the network by tremendous amount of effort. It is very difficult to map. You can that which tank is fitting to which zone, and you can see the path that has led to here. So tremendous amount of long distance this particular tank has to serve. So there are no district metering areas. This is theoretical, really, achieving district metering areas in such a situation. And all, if such a situation, all tanks are interconnected, no control on withdrawal. Even if you assume 10 liter per minute as a flow, multiply by number of connections, and you can estimate on a some simple back of the envelope how much withdrawal capacity your network has. So there is no discussion about that how I can control and how I can achieve the greater supply hours. Just imagine the supply withdrawal from this particular network. So within 1 hour, network can withdraw 2 times the demand. That is the situation we are living with. So how we are operating our city then? So what is typically operators are doing is they are creating small zones and opening one wall, supplying for 30 minutes here, closing that wall, and again opening the another wall. So part of the distribution is getting very high head loss because now you are trying to push a 24-hour demand in 1 hour or 30 minutes. That causes tremendous amount of problem in the distribution. So that we need to understand and then plan the entire design. So whether the current hydraulic modeling is realistic, because what we are doing is many DPRs I see people sit in the office on all the roads, they lay the lines, show on the hydraulic modeling, everything is green. Anyone who can do a simple computer simulation can do this. Add as much required water in the tank level, assume that people are closing the taps, demands are satisfied and all that. That is not what is going to happens in the real. So we have to, this is prevailing demand driven modeling approach. That is one of the hydraulic modeling approach, and basically all the DPRs are prepared using demand driven modeling approach. But when they're implemented, there is pressure dependent behavior. So we have to understand that all our DPRs are presently based on demand driven analysis. All the scenarios are demand driven analysis. That means demand is assumed to be satisfied irrespective of residual pressure. So whether there is a 2 meter of residual pressure or 10 meter of residual pressure, it is assumed demand is always satisfied, which is not true, right? If you understand how the system behaves. So there is a concept called pressure driven analysis where it is assumed that demand will vary as per the pressure. So as the pressure increases, the demand is also increases. So that is also not the reality, because in reality, we have different outlet properties. Outlets are, there are tanks or there are taps which do not have any meters, and people will always have this particular taps open. So demand plays no role in this particular outlet property based pressure driven analysis. So a lot of research has been happened on outlet properties based pressure driven analysis, and withdrawal is strictly dependent on pressure and outlet properties. So what is the pressure in the system and what is the outlet property of the model? So service connection size, length, elevation level, those things we should consider. What we have developed further is most of the networks are flow starved. That means there is no enough flow in the network and we are operating those networks, and which is the most common situation in intermittent water supply. So we have developed, Abhishek developed this particular hydraulic modeling approach for evaluating the performance of flow starved network, which is recently published in Intermittent Water Supply special issue in Aqua Journal. So what we have done is, basically we have taken into account the inlet and outlet properties of the network. So basically in the transmission network, you have MBR, water transmission network, and ESR. In distribution network, you have ESR, water distribution network, and consumer system. So what we have done is we have modified the tank configuration itself. Typical hydraulic models will stop giving results when level hits the low supply level. But this particular modeling approach will give you result even water will be in the standing water column, this particular zone. And we have also characterized this particular outlet properties by implementing control wall, and we have converted the demand nodes to reservoirs. So there is no demand because it is very difficult to predict demand. So we have assumed all the nodes are reservoirs. So they can basically take out the water as soon as it is supplied. And that's the reality we are living with. So basically we are filling one tank to another tank, even in the distribution system or in water transmission network. So this kind of hydraulic modeling method we have developed, and it is tested on a real life network in Bada Pokhran multi-village scheme in near Palghar, near Mumbai. Based on that, we have first of all proposed the performance indicators, because what typically people talk about residual pressure or supply duration, but those are not sufficient to understand IWS behavior and performance. So supply duration is one of the criteria, but do not capture the internal variation. So our work has proposed, Abhishek has proposed two output-based indicators. One is flow-based demand satisfaction, that what is the flow delivered and what is the demand. So flow delivered in LPS and demand in LPS, that ratio you can monitor. And volume-based demand satisfaction ratio, how much volume, let's say how much total liters you supplied and what was the total liters demand was available. These two indicators will tell you how system is performing. Okay, so those are very key criteria need to be incorporated in the performance of the system. So flow FDSR and VDSR. So FDSR helps in tracking deviation from design scenario and can be used to assess bottlenecks and excess withdrawal network capacity. And VDSR helps in assessing operational strategies, that how I can control the withdrawal for different zones that can be used. So using this and using our method, we have performed the hydraulic modeling, hydraulic analysis, and most of the models, if you see, will show that there is equity in the design, when you analyze the initial scenario. But our method shows that when you use this particular flow starved pressure dependent analysis, some nodes, some tanks can withdraw 11 times, 12 times more than the designated if there is no control. And mostly our systems are operated where there is no control on the withdrawal. So there is some nodes without receiving any water, some nodes receiving tremendous amount of water, and that's the behavior, starting behavior. So this is the 50% of the reality. I'm not saying that this particular modeling approach will give you the exact behavior, but this is initial understanding of the system, which our current methods do not give you, because those assume the different scenario than the actual on the ground. So this particular method allows you to incorporate the actual behavior of the system. So use this 50% of the knowledge and then 50% on field. So a lot of field work we have to do. We have to monitor the pressure, we have to monitor the flows in the network, and then take the decide on the intervention. So some of the things we'll discuss that. What we propose is use Jal Tantra, which is a free software from IIT Bombay for optimal design of pipe water network, which use basically linear programming, integer linear programming approach, and use EPANET, combine them for analyzing this system. So our paper has some sample networks also. So people can use that for designing and analyzing the our intermittent water supply. So this is completely, both of these softwares are freeware. So should we how we should change entire this strategy of hydraulic modeling or design? So as per manual, we are supposed to consider this, but we have in between storages, and people will not go away with this. Historically, people have invested into storages because there is no reliability in the transmission network. There is no reliability in the electricity grid. So we're not sure that tomorrow water will come. So in rural areas in near Mumbai, this is the situation. People have to store, and this is from all these buildings have underground huge storage tanks. So whether it is city like this or a rural area, storages will be there. So hydraulic designs models have many data gaps. So don't too much believe. Even I'm saying our approach, I told you 50% you can believe. So do not believe on hydraulic model and take decisions because population forecasting, network details, Hazen-Williams, demand allocation, DD or PD approach, tremendous amount of uncertainties are there. So we have to go on field, do the entire monitoring, and then take the decisions. So based on this lot of theoretical analysis, I'll show what should be the aim now. So whatever problems and issues I've told you, what should the aim of pipe water supply is? We should aim for a water supply system that can supply water reliably. Reliably means every day, fixed hour, if I can supply, 1 hour is sufficient. If you supply with 10 LPM, my 600 liters per household will be the demand typically. So, and equity, that everyone should get this, not that only the low-lying area or prime area. So reliability and equity, which will require less monitoring, which will consume less energy, easy to operate, minimum need for automation and ICT. And supply hours can be adjusted based on source average. If you have a good source, go for 24/7. If you have reduced source, there are issues, you can design system accordingly. So, and water quality management can be, you can, in Safale Palghar, we are doing a lot of work. People have segregated their drinking water problem from pipe water. They have their own system, community-based filtration plant where they are taking water from for drinking, because only 3 to 5 liters is required for drinking. So we have to take the decision and save the cost of achieve the efficiency. In this direction, we have done some of the innovation and strategies we have developed for improving water supply. So there are innovations based in planning and design and operational interventions, like small scale tanks, multi-outlet storage tanks, optimal design, head dissipating devices like manifold shafts, and pressure management. So the entire effort has to be matching withdrawal with the design discharges. If any hydraulic designer achieves this, then they are understanding their system. So let us see how we can achieve this, and some of these innovations I will introduce. So first is focusing on decentralized infrastructure approach. This paper I written in 2019 with Gokhale sir, who is retired superintendent engineer from Maharashtra Jan Pradhikaran, who has a lot of work done on field. So decentralization, why it is important? Because in today's time, we have huge tanks, huge pipelines, and we are stuck with that particular system. And many people will not believe that, okay, I'm recommending, or somebody from India is recommending, so it's not following. Even the US, Fire Administration Water Supply Guideline clearly writes small pipelines are required to serve decentralized storages. It is more advantageous to provide several smaller storages. So we have to follow this particular model if we have to come out of this particular vicious cycle. Else we will be talking about the same thing of creating large tanks. Now, many people will tell me there is no land in the tank for the tanks and all. I will explain that also in some moment of time, how we can innovate there and create, at least try to realize this this guideline or this approach that we are recommended in this paper. So first is deciding influence zones of the reservoir of your storage tanks. So typically the storage tank is 15 meter to 20 meter in height. We have to maintain 7 meter as a residual pressure here. So how far we can go from here is very important, because if you just haphazardly start increasing these zones, it will create tremendous amount of problem, and whoever was getting water will not also get, and people will start using household pumps. So if you typically any software you design 3 to 5 meter per kilometer hydraulic loss will be there, whether you use Jal Tantra, whether you use any commercial tool. So how far you can go is about 1 to 1.5 kilometer. So this influence radius and influence zone you have to consider. And based on that, what we have come up with the guidelines for different cities, what kind of storages we can recommend. So for Mumbai, which has very high density, we have 1.7 million as a storage, decentralized storage scale. Hyderabad, Delhi, Pune. But if you see, it is 0.3 ml, that means 3 to 5 lakhs. What Pune is going for is 20 lakhs storage tanks. Mumbai is going for 80 to 90 lakh storage tanks. Now, people will say there is no space and all. I'll show some of the innovations we can do here. And then class 2 cities. So this is just guideline. I'm not saying this, everything has to be reflected on the ground, but the direction of thought has to be this, that you have to maintain an influence radius, influence zone of the tank while planning the new DPRs. So first recommendation is small scale decentralized infrastructure. So why small scale I explained, and then using multiple outlets. I have seen many tanks people are doing with only one outlet. I think we have to stop that. We have to create the multiple outlets so that different areas receive water differently. So this particular one simple solution is to convert single outlet to multiple outlet. Even existing tank can be converted using manifold, that I will show, and new tanks should definitely have this. So this will help in maintaining the influence zones. Reaching consumer is a key, because now these consumers, if they will not be affected by behavior of these people here. They are basically connected to different outlet. So this kind of design enabled zoning we have to do. And this is multi-outlet reservoirs already installed in some locations, but it is not uniformly used. So we have to make it as a practice. So what are the benefits? Flow diversion is achieved, time staggering is possible, and minor additional cost per outlet is required, which will be compensated by peak damping, because you have multiple outlets now. So what I'm suggesting is you have MDR and ESRs and do the multiple outlets. So Anuj did this particular analysis research on comparing single outlet with the multiple outlets. So we have taken 2 networks, converted single outlet to the multiple outlets. One is in Kolhapur in Amravati region and Ratnagiri in Konkan region in Maharashtra. So what happens if you convert single outlet to multiple outlets? So you can see on all fronts, multiple outlets, which is in blue here, performs very well. So this research is also published as part of his PhD work. And we have considered the intermittent scenario. So typically what we assume is 1.5 or 2 times the ultimate stage demand. If you run from the network, what will happen? And in that scenario, multi-outlet performs very well than the single outlets. So this research, so all whatever recommendation we're making is based on a lot of research that we have done in last few years. So this Urban Water Journal, this publication is also there. So result is there are tremendous amount of operational benefits, operational flexibility. So convert this single outlet to multiple outlet using manifolds, or any other new tanks can be converted from the planning stage itself. So the slum areas or high-rise areas can be segregated, different land use can be segregated. So this is one recommendation. Now, how to overcome with the standing water column, which I explained in the previous slide, that we are facing with this issue of drawing the level too much here. Professor Bhave Gupta has given a lot of recommendation about using orifice and flow control walls. In our paper, we have used manifold and masterpiece for with controlling the withdrawal and using shaft. So I'll introduce shaft as a concept. So shaft is where we use this particular element, hydraulic element, where water comes from this inlet, goes up. There is an annular space where water will fall, and we have multiple outlets. So this element you can add anywhere in the habitation. So it doesn't require much space. So you can go with the available hydraulic energy nearer to the consumers. That's the benefit of this shaft. So this will be used for maintaining pressure at the tail end, emergency or temporary ESR, to provide achieve liquid distribution. So a lot of benefits can be possible. For example, you can have the different outlets from this single, and you can at the corner of the road, this shaft is constructed by our team in Safale Palghar. I will give you the details in some time. So different HGLs will operate from the same tank for different outlets. So what I'm suggesting is, because these tanks which we are constructing are basically getting emptied, and because of withdrawal is too much, because there is no control on withdrawal. So municipalities and rural areas are bypassing the tanks. So what we are suggesting is to add a hydraulic element called shaft in between like this, which will maintain the pressure. And in the how it operates, water comes in, falls in the annular space, then we have the multiple outlets here. Hope the people are understanding the concept, or we can discuss later if there are some doubts. First study we did with this particular idea and analysis is in Umbarpada Safali in Palghar district, Maharashtra. Many people must be knowing. Here is the Palghar district in Maharashtra, and here is the Safali, which is emerging town, has 30-40,000 population. So Karwale Dam is the source of this particular area. So when we visited in 2017 as a part of a DST funded project, this tank Safali ESR 1 lakh liter capacity was not operational, and the operators were bypassing this tank because this tank was leaking. There was huge leaks in this tank after few years of operation. So what they were asking is to construct another tank. What I suggested is, let us try shaft and let's see the results. So means the Gram Panchayat agreed, Safali Gram Panchayat. So we constructed the shaft. First, we monitored the entire area. You can see a lot of multi-story buildings also here in this particular area. So we took, so existing tank was in this area. So they were taking water here and again bringing back to the habitation. Instead, what we did is we constructed a shaft on the way to the habitation itself. And these two zones we planned, Safanagar and Andare, and few more outlets we have kept for future use. So what we did is, from the transmission line, they were operating these two lines by bypassing the tank. Okay. So we use this one pipe as an inlet to the shaft, and this shaft was constructed. We gave the drawing to the local fabricated, local fabricator and local people have used. We have painted it in the local conditions, and you can see the date. This is in 2020 November, just after COVID. We started actually implementing, and it has multiple outlets. You can see. So the inlet pipe is here, and then the multiple outlets are here. And this shaft is now functioning for last 2 years and 2 months in Safali Palghar. Commission handed over to Gram Panchayat. They are using. We are not also there now. We have monitored this scientifically, and this was completely funded by Department of Science and Technology. So shaft height can be 12 to 16 meters, depending on even you can construct up to 20 meters or more. And outlets are we can keep 1, 2, 3, 4 outlets. This outlet 3 is for future purpose. So you don't have to again do everything new. So you have the another outlet available. So this you can see the December 2020 we have commissioned this shaft. Anyone wants to visit can visit in Safali Palghar, 90 kilometers away from Mumbai. So entire Gram Panchayat and my research team were involved. We operated this same system by our own hands, monitor this data. Based on that, all of these particular recommendations we are making. So we have monitored the data, and we could able to deliver the same service. Even we could reduce the standard deviation. So we brought the more equity in the system by adding the shaft. So what are the benefits? We have gone closer to the habitation. We use a very minimum area, and we have constructed this at a very low cost. The new tank would have cost 40 to 50 lakh rupees. The shaft we constructed in 8 lakh rupees using DST funding. After that, we got a lot of inquiries after we disseminated through media. So ROTAG is one of the initiative at IIT Bombay, funded by Principal Scientific Advisor of Government of India. So they have funded this shaft through NGO in Takpada, Palghar. This is also one shaft. This is in my hometown, Kolhapur. Kagal actually is my place, where we installed this particular shaft, where people were not receiving water for 10 years because they were using GSR. Pressurized pipe was there, but they're putting this water here. Instead, we just use shaft using minimum investment and avoided the elevated storage tank. You can hear this video.
आता आपण हा शाफ्ट टाकीच्या ऐवजी बांधला. टाकीची मागणी होती पूर्वी, ESR बांधायची मागणी होती. त्याच्याऐवजी आपण हा शाफ्ट बांधला. त्या शाफ्टमुळे आता काय फायदा झाले? शाफ्टमुळे लोकांची पाणी प्रेशर घेतलं जाते आणि टाइम वाचतो. किती टाइम वाचतो? पूर्वी किती सप्लाय? पूर्वी 1 तास, 1.25 तास लागायचा. आता 40 मिनिटं, अर्धा तास लागते. तेवढं तुमचं पूर्ण कव्हर होऊन जातो. काही असा तक्रार नाही. तर हे तुम्हाला त्याच्याबद्दल तुम्हाला ऑपरेशनलाही सोपा आहे. हा
सोपं आहे, काय अडचण नाही, एवढं काय अवघड नाही.
तुम्ही किती वर्षापासून पाणी पुरवठा करता या गावांना?
15 वर्ष झाली.
15 वर्षाचा यांचा अनुभव आहे. गेले 15 वर्ष हे पाणी पुरवठा करतात या भागामध्ये. हा शाफ्ट लावल्यानंतर त्यांचा जवळपास एका झोनसाठी 30 ते 40 मिनिटं वेळ वाचतोय. आणि प्रेशर सुद्धा वाढलेला आहे आणि लोकांचा खूप चांगला त्यांना रिस्पॉन्स मिळालेला आहे. तर अशा प्रकारचं तंत्रज्ञान जिथं आपण टाकीच्या ऐवजी शाफ्ट, टाकी बांधायचा खर्च 30 ते 40 लाख रुपये असू शकतो, त्याच्याऐवजी आपण 6 लाख रुपयामध्ये हा शाफ्ट उभा केलेला आहे. आणि हा मेंटेनन्स फ्री आहे, वापरायला सोपा आहे. पंपिंग आवर्स कमी झाल्यामुळे एनर्जीची सुद्धा बचत होते, लोकांना सुद्धा समाधान मिळतं. अशा प्रकारचा हा नाविन्यपूर्ण आणि एक शाश्वत प्रकारचा प्रोजेक्ट आहे. किती वर्षांनी पाणी मिळालं तुम्हाला आता?
आता 12 वर्षाची पूर्ण.
12 वर्षांनी. 12 वर्ष तुम्हाला पाणी नव्हतं?
नळच नव्हता येत.
नळच नव्हता.
आम्ही
खड्डा
हातपंपच
काढून सुद्धा पाणी येत नव्हतं तुमच्याकडे?
नव्हता येत.
आता पाणी तुम्हाला दाखवा केवढं पाणी येतं तुम्हाला आता. अगदी या एवढं पाणी आता येतं यांना आपण शाफ्ट बसवल्यापासून. तर सगळे आता तुमचे प्रश्न सुटलेले पाण्याचे, तुम्हाला पाणी भरपूर मिळतं.
असाच नेहमी आला पाहिजे.
हो, असंच पाणी येईल. आता तुमच्या समोर आहे बघा, समोर लागल्यामुळे तुम्हाला दिसेल.
So that was one success story we have, and there are many stories now coming up in Dandi Palkar. Now we have startup company who's doing all this work because a lot of inquiries are happening. This is one of the another very innovative project in again tribal region in Thane, where the cost saved due to tank is invested into solar panels. So there is no operational cost also. So this was inaugurated also in 2021, and the current chief minister was there to inaugurate. So the model for rural areas is that you pump from the source, river, groundwater, have the online water filter, use the shaft for the distribution, and close the supply. So that in 1 to 2 hours, the water demand will be and the cost saved will be used in the solar panels. So that's the idea of sustainable water supply for rural areas. So benefit of shaft: equitable supply, open to sky, multiple outlets. HGL varies as per demand, less movable parts, cheaper than ESR. So these are the benefits of this shaft. For cities, now many people will be interested in what we can do in cities. Is you have the ESR and convert that ESR to the shaft by adding shaft into the distribution system. So you can have the express feeders and bring to the shaft. So we are working in Dahanu city where we are actually implementing this model through CSR fund provided by Stem Water. So this is the model we are working for the cities. Okay, so we have filed the patent. We have startup company. This technology is transferred to this particular startup. Beauty of this is that we have the flexibility in the system. So the HGL will be decided by the system. As I told you, nobody can predict the demand at the particular hour. So shaft gives you the HGL adjusted hydraulically automatically by the system. So this we want to scale up at a very large scale. Then we worked on the manifold system in West Bengal. This case I'll show, and then maybe you can have question and answers. What is happening in most of the distribution systems is these large diameter pipelines, when they go and when the withdrawal is too high or there is a steep slope, pipe run partially full because of, and then there will be air entrapment because of sagging pipes, and many issues will be there. So unless we address these issues, no amount of energy or pumping will help us. So this may be open channel flow, create air entrapment, and part of the system will be pressurized. So what manifold is, basically you convert this particular pipeline to 3 different pipes of 1/3 area. So this is, let's say, 900 mm pipe. This may be around 200 or 250 mm 3 pipes you can use, and only for first 10 years you operate this. These 2 walls may not be operated for first 10 years. When demand increases, then you operate this, and then in the ultimate stage you operate this. So this is the principle of using manifold, and you can have a lot of fine-tuned pressure gauges and air walls to take out the air. So a lot of such manifolds were used in 156 multi-village scheme in Amravati, but replications have not happened. So this particular model we are working for distribution systems now. So one such case we implemented in West Bengal. I'll explain the application. So application is in Dongara region, in this region of West Bengal, because West Bengal Public Health Department called us for working with them to solve this issue. So they had this is in 24 South Pargana district. So they had a zone 9, and it is a multi-village scheme. And in one zone where 9 lakh liter capacity tank was there, 20-meter staging height, but water was not going ahead. So service reservoir was located somewhere here. First, what we did is we trained the entire PhD with this concept of shaft and manifold. I went with the idea of shaft, but then appropriately I found that manifold is more suitable there. We, as I told, partly hydraulic modeling, partly field work. You can see the entire chief engineer, Animesh Bhattacharya sir, and entire team. We work together on ground and monitor the entire system to study what is happening. First of all, even if there is a head, why we are not getting the water. So what we observed is, because the initial design, as per 3 peak factor, only one outlet was kept. The head loss in this particular premises, CSR premises itself was 10 meters. So what I'm saying is, if this is the premise of the ESR and this is the tank, only the premise, because of this huge head loss in the single outlet, then the branching will occur after the premise. But in the premise, tremendous amount of head loss we observed, 10 meters of head loss. So your tank basically operating at this level. The head is not utilized. We are basically wasting the head. So these simple findings you can have. So we monitored the entire system. You can see amount of pressure points we took. We monitored what is happening. Even using this hand pump, people were not getting water. They used to struggle a lot. So the reservoirs are here. Another issue was the planning. So the entire planning was not correct, because this entire region was planned on one single 9 lakh liter capacity. So you can imagine how far water can go. This is not magic, right? It cannot go like this. We have to plan for this. So decentralized infrastructure. Instead of 9 lakh liter, if they have constructed 3 tanks, 3 lakh liter capacity, this situation might have been avoided. So when we monitored, only this area was getting water. Rest of the people were managing somehow with other sources. So even if Ganga river was there, but they were not getting water, that's the irony of our situation. So this, what we first suggested is to convert single outlet to multiple outlet. So we asked them to install this manifold. We gave the design, and very promptly, very actively, they have installed this manifold. Then we asked them to do the zoning. And after this particular effort, water started coming in many areas. So again, the executive engineer and the team was there to see the commissioning and the results. So what we observed is, with the investment of let's say 25 lakh rupees for the manifold, earlier they were planning for a very big investment of for this particular area. But with this small investment, we could convert this low pressure to a high pressure system just by converting single outlet to multiple outlet. And when we monitored after the implementation, this much area was getting water. Still, there are areas. I told you, this is not magic that we can solve everything. We will have to do work step by step. Now there are outlets, remaining outlets we can use in this particular manifold. There are some spare outlets we have kept. Those can be used as express feeders to these areas, and then using shaft they can be distributed. So we have given this proposal also to them. So the spare outlets are there. And you can see the pressure before an outlet after. So and this is one feedback from the consumer.
क्या बोल रहे हैं?
बोले पहले नहीं आया था,
हाँ।
थोड़ा थोड़ा आता है, इसके बाद अभी पानी ज्यादा है।
अभी हमने आज से ना, आज से चालू है।
हाँ।
कल नहीं था,
आज ही के बना
परसों
कल
आला जब हमने चालू किया था। ओके, तो जब
So when we installed the manifold, the water, this lady got water after many years, because there was no water reaching even with the hand pumps. So this we have also installed in Safali Palghar. This is in Malkoli, Bhivandi, where we converted this air wall to this manifold system, and 14 meter of pressure increase was there. So very simple innovation which is added. So what I'm saying to the cities is, convert first of all this single outlet tanks to multiple outlet using manifold like this. Nearby area can be given by one outlet. Other areas can be given by the express feeder and shaft. So we want to work with many utilities and cities to realize this model on ground and see the difference. This is to be tested. So whatever work we did with West Bengal government was published in Minister of Jal Shakti Samwad Journal as a success story. The Minister of Jal Shakti has given directions to all the principal secretaries to use these innovations, try those innovations, and we will be happy to work. All the small cell tanks, multi outlets, manifold, shaft, they have given their so this is in public domain. This particular advisory they have issued. Non-mechanized water treatment plants, very useful for rural areas. Jal Tantra, pipe in pipe. Not all innovations I have discussed, only few. I think enough time I have taken. So now we lot of inquiries are happening. So we have this startup company. IIT Bombay has permitted us to have this startup. So Anuj is looking after this particular startup, who himself has worked on this shaft as a concept. So in summary, a water supply system can supply water reliably and equally with a tap flow of 10 liters per minute. So if we aim for a very simple thing, I think we should achieve this first. If, instead of jumping directly to 24/7 or any other new terms that people are coining. Low cost innovations. There are many innovations I've seen ground engineers are doing. We have to adopt them. Decentralized infrastructure, alternative pathways of water provisioning, we have to adopt. First step is pipe carrying the bulk water should be always charged, operating 24/7. Many cities I see that it is not charged, and then people are planning for 24/7 projects. It will be always a failure. If that is achieved, then the second step of restricting the water withdrawal as per norms. And then only you can jump. If when you have the people consuming water as per the norms reliably and daily basis, equity is there, then we can plan maybe 24/7. But then we have to see the need whether people really want, because many cities people are also objected to 24/7 experiments. So I think that's what I learned through a lot of this particular research and my work with my students and many public health engineering departments, cities, Municipal Corporation of Greater Mumbai. So a lot of this research is funded by DST. We have received generous funding through a variety of programs. Then RUTAC IIT Bombay is now an implementation partner for shaft in rural areas. STEM has given us tremendous amount of support for through CSR funds for realizing some of this innovation on ground. And Coal India Limited is also has given CSR funds.